Okay, the main part of chapter 5 is intervals, definite and indefinite. And what of this particular section of calculus. And what we're going to be doing is a little bit of drudgery, but it's very vital as to how integration became easier and more accurate as time went on. And we first visit estimating area with finite sums. Now, the key to doing these items was the fact that in the first part, we're looking at values that are on a defined interval, but it's not structured as an integral. So we're going to first visit the concept of area. We understand that area of a rectangle is known as a capital A equals length times width, because it's a rectangle. And more loose rectangle, and we force it to be one like a parallelogram, we know it is width times height. And this is the one we're talking about, the height. And that is, for us, the Y output. And so we're looking then in reference to an enclosed area under a curve. So what we're saying now is the fact that we can have this condition here, and we want it from, say, 0, and it's never large, to, let's say, 3, and we want this area under this curve. Well, the concept was to find rectangles within with an equal distance. The more rectangles, the more accurate, because either left in or right in, which is we're going to get to, we're forcing rectangles to take place. And we're going to draw some so that you can see it was a más o menos. And the partitions that we're going to do for this particular section is even, 2, or 4 only until we get to Riemann. Because Riemann came about and said, well, shoot, we ought to make it infinite many, because the more rectangles we have, the more accurate the area. All right. So we're understanding now that area is going to be the length times width, right? So it's going to be the delta x and the f times the y value, f of that delta x. And we're talking about one partition, and delta x is constant, to the second partition till we get to the end. And nothing hard, very little math, and concept-wise, it's very, very crucial. So here we go. We're going to always keep it easy. The homework is 8 problems. 8. All right. So here we have used the finite approximation to estimate the area under the curve of f of x equals x squared. And above the graph of f of x, that's above the y-axis, of f of x equals 0 to 12. All right. So we have a parabola. In the parabola, if we understood, what we have here. Let's do the middle. This is a 6. All right. So if I have 0, I have 0. if I have 6, all right, in the parabola is 36, twice 36 is 72. My gosh, well, that's 144 times 2 is 288. All right. So we'll be using our calculators quite a bit for this particular exercise. And we're going to talk first about the lower end of that construction of what we have. Right here, we have 2 partitions. The delta x is the constant width that's measurable between those. And what are they? 6, right? So we understand that our width measurement is delta of delta x is 6. All right. So we did that. We could have done it by saying 12, because this is a closed interval of a, b, and we could have done it as b minus a divided by 2. Well, that's 12 minus 0 divided by 2, therefore it's 6. Okay, either way, but these are so easy, you know, just for an instructional purpose. Okay, so we've got our delta x, and now we know then we're going to construct our sums of each partition. In this case, it's 2. Right. And the lower end or the upper end, in this case, it's the lower sum. So nice. So the lower sum is this one right here. So let me do that. That's this one and this one. Now, what do we see automatically about this concept here? What's wrong with it? Yeah, we lose a lot of area. Yes, yes. And the use of the left and the right depends on the type of function you have. Because if we had 1 over x, it would have been perfect to use the lower versus the upper, because it's approaching 0. So, so it all is visual, all right? Well, let's talk about the definite integral. This is from 0 to 12 of our function 2x squared. Well, we would add 1 and divide by it. And then we haven't really learned this process, but it's very friendly. If I guess I could say friendly. And then we would do 2 times the 12 cubed divided by 3 for the 12, and then subtract the 2 times the 0 cubed divided by 3, because it's the upper, the b, insert a minus the a. And this, and I forgot to put this, because I'll have to have dx, because dx is delta x that we're looking at, that change or the size of the partition. Well, in an integral, it's infinite. In an integral, it's infinite, and we get pretty accurate on that guy. Now, I'm going to do the math on a calculator because my brain is dead. So here I go. Okay. So I'm going to have 2 times the 12 squared divided by 3. And we get approximately, what, 96? Approximately. Okay, if I did the math right.
It's supposed to be 12 feet.
I'm sorry?
Square. It's supposed to be 12 feet per square.
Oh, doggone it. And that's why I did the calculator so I wouldn't make a mistake. Sorry about that, guys. Thank you for that. Sorry. It makes more sense now. Again, area is primarily approximate on word shapes, but let me see what I. Thank you, thank you. Okay. All right. So we have this as a benchmark, and we know we're not going to reach it using what we just have, but we're going to do what we need to do. So the area of our function is going to be our 6 times f of 0 plus 6 times f of 6, because those are the lower ends. And we know we're missing a lot. So we're going to have 0. And f of 6 is, let's just do it, that's 36, 72. So we've got 432 square units, which is way off. And we know it. Okay. Well, then it says, well, what if we do 4 triangles? Well, the more triangles we enter, the better the outcome. So let's see what 4 does to us. Not drawn to scale? All right. So let me get my calculator out and we'll enter that. So for sure, I won't make a bobo. It's always an option. Here we go. Okay. So at 3, I've got 18. At 6, we know is 72. At 9, we know it's 162. And at 12, we know it's 288. All right. So we have our values. And we're going to do 4 on the lower. So if I do that, I'm going to have and the parts are 3. Delta x is now 3. All right. 0, 3. Oh, I left one out. 6. So I should have 4. No, 12 is an upper. These are lower. And I have 4 partitions listed. Again, on this guy, I have the 0 going on for the lower. For the lower, for the ending in 6, I've got this guy. And for 6 to 9, I have this rectangle. And from 9 to 12, I have this rectangle. And you can see there's a little bit less, that is not included. Again, it's still too short. Bless you. I totally get that. So on this guy, I'm going to have 3 times the 18. I'm going to have 3 times the 72. And I'm going to have 3 times the 162. Okay. So 3 times 18 is what? 40. What is it? Sorry, 54. And 3 times 72. Okay. And 3 times 162. We have that one. 360. No, I don't. What is it?
486.
486. And what is my sum? Okay. So even if we added and divided by true, we're still not even close to what we calculated as the area. So, okay. So before Riemann, they said, all right, well, let's cut them. Let's do the upper. So again, we're looking at our first one and we're going this way. All right. So this time, this is our rectangle. This is our rectangle. What is the problem here? Too much. Too much. Okay. So, I mean, this was the process that these guys did in order to figure out what would be the consensus of the mathematics to arrive at Riemann and then into integration. So we know we're going to get way above, but we want to do it. And again, this is 6. Our delta 6, delta is still 6. All right. So on 6 times our f of 6, we had 72. On 6 times this guy, which is 286 times the 288, we're going to have a big number. What do we have? 1,000. Thank you. So this one is over, as we knew it would be. It would be. So again, we're going to do more rectangles of the upper. I should say partitions, but I put sections. Bless you. So our area for our function is going to be, now this time delta is 3. Delta x. And here we include the 12. Because of 0. Exactly. And this is going to be very monumental when we get to the other part called the norm. When we talk about norm, the sizes of the breaks that we use. Because Riemann even said that we could judge it by whatever partition size we wanted, so long we were genuine as to how we calculated the area. So, okay. F of 3 was 54. of 6 was 70, oh, I'm sorry, 216. And of 9, it was, wait, I've skipped one. Of 6, 6 was, oh, I'm sorry. Let's see, I got the 3. The 6 was 216, and the 9 was 486, is what you all told me. And now we need the last one. So what is that guy? We had 288 and times 3. 854.
60. Oh, no, just for the 3 times.
Oh, you did the whole thing?
Yeah,
Oh, I'm sorry.
not the whole.
I'm sorry. Okay, well, let me just do the math. I was trying to get away with it. Ah, I hit the answer. Sorry. We get 1620. It's less than the 17, but it's not close. What happens with this is that we then change it to the midpoint. Now, I'm not going to do that one on the midpoint, but you can see that this is not a good form to do that on. But you must be able to do it. So what we're going to do now is a plane parabola using midpoint. Now, I think I do a number line because it's just easier for me, because we've got a 1 and a 2, all right? And we want it in 4s, 4 rectangles. So if I want 4 rectangles, I'm going to have 5 partitions, right? So this is going to be 1.5, because that would make it that. And then this would be 1.25, right? And 1.75. Does that sound right? Okay, so that makes delta x what? A quarter, or 0.25. And I do it this way just because it's easier. I do fractions more than I do decimals. What? I have 7.5.
No, we're not dividing.
Hiding, honey. We're getting the average, the middle point. Am I good? All right. Does everybody see that I just cut it in fours? Yes. Okay, good. All right. So this, okay, are my 4 partitions, but I'm not done. I need the center point, which is what you're talking about. First, I have the partition. This is partition 1, 2, 3, 4. Now I need the half. And so that would make it, and fractions work better for me. So I have 1/4. I'm sorry, this is 5/4. I apologize. And this is 7/4. And this is 9/4. And this is 2. Okay, well, I need in between for the midpoints.
Yeah, it's 6/4.
Yeah. And so it's eighths, right? It's eighths. So if I had eighths, eight,
Fraction for one point
uh,
five, correct?
is,
Yes.
okay, what did I do? Okay, I multiply by 2, 14. Eight. Oh, that's where I went wrong. Gosh, because I can't get the numbers to fly. Yeah, because I was giving you the answers to what I need. My brain was in Twilight Zone. What can I tell you? Is that right now? 7 fourths, 1/4, 8. Yeah. Okay. Eights. These are all eights. So the midpoint is going to be 9/8, 11/8, 13/8, and 15/8. Okay, these are my midpoints. Yes, a lot of little math. You can keep it in decimals. It's just easier for me to go with fractions. All right. So now that I know that, and I have the 4 partitions with the midpoint, and I know my partitions are 1/4, area of this function in 4 partitions is human fractions, I mean decimals, and it'll work because it's eighths. The decimals are pretty. And we're going to stick that all in the calculator. Type in something wrong. 1/4, 1/8. Yeah, yeah. Because these are F of. Sorry, I forgot my F. I forgot to write the F. 3, 8. I forgot the F. I'm sorry. Okay, well, we said, uh, if I did the math right, hopefully I did, we said that if we did the integral from 1 to 2 of our area, we would have x to the 3 divided by 3 from 1 to 2. Well, the 2 would be the 8/3, wouldn't it? Subtract the 1/3, 7/3, and it's a 2. So I'm pretty close. Pretty close, unless I did something wrong on the math. Yes.
How do you know when to stop?
Uh, Before you reach the last unit. It's a, oh, in each case it's been 1 to 2, and then I converted all of our partitions. And at that point, I found the mistakes. And I had to, whatever panel or decision you make on doing that is a personal math preference. Personal math preference. I told you, fractions work for me. All right. One of the things that we do in mathematics is figure out the distance equal velocity by change in a uniform way. Notice that they use subdivisions of the interval, and we're given that again time is what consistency in gradient. If you're checking on velocity, you're checking at a specific time that is uniform. Okay, so and that's again high school math, and then the way of analyzing what is happening in terrains that are not even, where velocity is affected by gravity or a wind or some condition that hits. So you want to know what total distance happened during these intervals. If you're a race car fanatic, uh, all of that's done by a computer that's in the car that's throwing it to the feed that the person is looking at how fast they're turning on the turn and what acceleration speed was done to get to the next minute of driving. And that's to measure the performance of the petrol that they're using, because it's really weird stuff because it's very flammable, and other concepts, and the tires. Why do they change the tires? Hot. And they will expand and blow. So they're doing all of this on computer screens if they're really worth their salt, and making sure the driver is aware of it, because he's always connected. And he said, "You took that turn at blah blah blah, and not good. No, you're gonna wreck. You're gonna lose the tread and hit the wall." Velocity on a turn can get you airborne. That's why they say go on this curve at 20 miles an hour, right? But we're all escapists. So okay, here we go. This is easy stuff. The table shows the velocity of an object, centimeters per second, at each second as it moves along a track of 10 seconds. Estimate the distance traveled using 10 sub-intervals of length 1 second, and left end, and then the distance at right end. So on the left end, we omit the 10. And on the right end, we omit the 0. Well, the distances are going to be the what? Same, because both endpoints are 0. It's a halt. They stopped. But this is an exercise in knowing how to follow the rule. So we're saying here that we have on our distance, and the distance and time is always at 1. So we have 1 times the 0, 1 times the 5. Now, do I have to put 1, guys? No, I don't. But I am, because this is lecture. You just put all of this added to this number. But I have to be concise because it's by a unit of measure, and I didn't trick you on anything. All of your problems are by 1 second. We would add that. So we would take our calculator and add it. This is where I'm diddling. Oh, I did. Oops, sorry. $36, $22, $15, $8, and $5. Did y'all get that? And now, if we did the next one on the long side on the right, it's the same. All right. So this is our last one on this lesson, and I did the upper, and I forgot. Sure. So here we're talking a tank is leaking at an increased rate as indicated with the table below. Use the table to answer the following questions. Well, what I'm getting at is I left off half of the information. I think I did because it's upper and lower. Because you have to do a kind of balance on what we understand. Okay, so we had it should have been lower and then upper, but it doesn't matter. Just so long you know we have to do two of them. All right. Well, that was brilliant. Okay, so we're going to do the upper and the lower in reverse. It's after 4 hours. Well, after 4 hours is this group right here, the leaks. 550.
Like after these zeros to four, not 5 to 8.
Because it's been 4 hours.
Because it's been 4 hours. Well, that's how I understood it.
I thought that like you would take the 330. I put 330. 4 to 8 on this one. What are we going to do on the next project?
Oh, I see what you're saying. Yes, I would have to start on the 3 because I'm on the lower. But I started on the upper, but it's okay. I'll make it lower. I see what you're doing. I told you I wrote it backwards. Okay, I would stop at the 630. On this guy, which is the upper, I would start at the 410, then the 550, the 630, and the 20. Okay, does everybody got it? I just wrote it backwards. All right. Now that I see where you're thinking, and it's good. And in your homework, it's lower than upper. But you know, I haven't been feeling well, so it happens. So I got 2310, and the second one is, which is the lower. You can multiply by it, the same thing. That's what I asked you. What did you see? What did you understand? An hour. It's per hour. Okay, so I have the 2 gallons. It wanted lower and upper after 8 hours. All right. Okay, this time we're going to do the lower and the upper because we're using this guy for the problem. Okay, so on the lower, I'm going to have I'm going to add this guy. Okay, and on the upper, I'm going to add this guy. All right. So I have the lower and the upper total gallons lost in what we had. And it gave us these 2 problems. And it said, if the leakage occurs at a constant rate of 720 gallons per hour after 8 hours, the tank initially held 22,000 gallons. Uh, the leakage, okay. Estimate the least amount of time. All right. Least amount of time. So we're talking the least amount, which was this number here, because that was the least number of gallons lost for that percentage average, that the tank is empty in how many hours. So what would I have? Well, if this is the rate of change, because this is average gallons per hour, all right, and we have 22 gallons, and we're leaking at this rate, how would I figure that out? No, we have to use our numbers, right? So the least amount, okay, the least amount that we had was what? Well, in a no, because we have used this amount that we know of that we've lost, and add to that the rate by the hour has to give us how many total gallons. There you go. And now you would do that solving for hours. So we'd subtract tiny math. 720. And then we'd get some kind of decimal value. So let's see if I did that right. Little math is getting to me sometimes. Double checking, making sure I get you the right numbers. And it would take 27 and 2200. So our 27.2. Oh, wrong place.
And then we add 8 to that?
Nope. Nope. Already included it in this mileage. And the larger n would be our larger number. Because this is our average. Times this many hours to get the 22,000 loss. Was 26.3 because of the loss. It'd take a shorter amount of time. All right, that's this lesson, guys. Not difficult, a little mathy,